Hello, Heiko. This is my bonus mark answer for the first question. First off, I just drew a little diagram here. Just to get the idea of what's happening. We've got the boat behind the mountain, the projectile getting launched, going over the mountain. Mountain height will be the 1800 meters. And the middle point of the mountain will be 2500 meters away from the launch point. The right side of the mountain will come out 300, leaving us with an unknown distance here that the vessel can still be protected. We'll boat here. The angles, what else can I say? Just the general y and the x-axis, obviously a two-dimensional equation. And how I understood the question was, what distance away from the mountain can the vessel sit and still be protected? Obviously just going off the distance on the sea level. It'll jut out a little bit, but just going off the actual sea level. And I wrote down the questions. What's the max distance to the right of the mountain the vessel can be and not get hit? Which is obviously this point here. And find the maximum angle that the projectile can be launched and still go over the mountain. And that will give you the shortest possible distance past this mountain. Because as you see here, if you have a very low angle of the projectile going over, it's going to be quite a long distance. So later in the equation, I don't worry about that. Okay, I'll probably just keep that there so you can see the diagram still. I wrote down the stuff that we do know. So the distance that we have to come over is that 2,500 meters and the 1,800 meters going up on this mountain. The gravity, acceleration due to gravity, is obviously 9.8 in the negative direction. The velocity of the projectile at launch will be the 250 meters per second. The only thing we don't know, or besides the angle, is the time. And to start off with, I decided to put everything into the position equation. But to do that, writing's a little bit messy because I wanted to fit into one page, just so it's less fiddling through papers. I wanted to find something that can represent time very simply, so I can use that in the y-axis equation later on. So I put in for the x position. Obviously there's no acceleration on the x-axis, but there will be the velocity, and that will be, I wanted to make this the 2,500, so at 0.25, 2,500, it'll go the ratio of cos theta, where the start is 250 meters per second, and the time that it'll reach this point will be represented after you simplify the 2,500 over the 250 cos theta. That'll be the time will equal 10 over cos theta. And I put that into the y position formula on the y-axis. And that y position formula will be half acceleration in that y-axis times time squared plus the velocity times time plus the position at O. And the position at O is equal to 0. The y position at the time that the x position was 2,500 would be the 1,800, so I put that 1,800 in there. And if we come down to here, after subbing in the time in place of these here, I got 1,800 equals negative 4.9 times time, which is 100 over cos, since we did the squared, plus 2,500 meters sine theta over cos theta, because this 250 sine theta will be the opposite here, which is our trig identity for the length of this, if that theta is a certain number. And I did a little arrow here just so we can follow it a bit easier. A little bit messy, but it's all there. And we'll come down to this, which is just simplified from this equation over here. From this equation, I wanted to get time to be constant for both of the expressions. So a little bit of trig was involved. First, obviously, I wanted to make the easiest one to go first. So this sine theta over cos theta will equal tan theta. And because it's cos squared, I decided to make this one 1 over cos squared will equal sec squared. And sec squared equals tan squared. That's the only way you can really get the same expression for the t. And then if you expand that out, you'll eventually get the negative 490 tan squared plus 2500 tan theta minus 2290 will equal 0, with the quadratic formula to find the value for x, which I couldn't fit on the paper, but fairly straightforward formula to figure out x. We get x equals 1.7 after subbing into 10. After getting x, you sub into 10. For the x values, I got 1.197 and x equals 3.905, keeping that sig figs going. And then because we want the highest angle, we want the highest x value. If you got the lower x value, you'd be getting a very low angle that could possibly go over this mountain coming up here. So I didn't worry about the 1.197 because that won't give us what we want. And then the inverse tan 3.905 will give you 75.64 degrees. That's the theta maximum height, 75.64 degrees. That will be the maximum launch angle that it can go over. And that range, doing the velocity initial squared over gravity times sine 2 theta, if you plug the 75.64 in, you will get the 3065 meters. And this 2500 and the additional 300 meters will give you the total distance where the vessel can't be compared to this position over here. So if you minus those two numbers from the range, so 3065 meters minus the 300 and the 2500, you'll get 265 meters, which is a little bit bigger than the 300, but that doesn't matter. That the vessel can still be and not get hit. Okay, thank you very much for watching the video, and goodbye.